אוקיי, אז שלום לכולם. היום אנחנו מארחים את הדר פרנקל מה-Center of Information Security בגרמניה, והיא מומחית ב-Formal Verification Methods. זהו, תודה הדר.
היי, שלום לכולם, אבל שנייה עכשיו הסתבך לי בגלל שהקלטת, אז אני צריכה לעשות לו אישור, אני כאילו לא נותן לי לאשר כי העכבר שלי לא קיים שם, אז רגע, תנו לי לנסות, סליחה.
אין בעיה.
ניסינו לעשות הכל קודם, אבל... אוקיי, עכשיו שוב. יש, אוקיי. היי, שלום לכולם. אני הולכת להציג את ההרצאה שלי באנגלית, אני מקווה שזה בסדר. וגם לפני שאני מתחילה, אני רוצה להגיד שאם יש לכם שאלות טכניות שכאילו ימנעו מכם להבין על מה אני מדברת, אז לא להסס לשאול, כי אני לא רוצה שתהיו עבודים בהרצאה שלי. אם אני אראה שזה נהיה יותר מדי, דיון עמוק מדי וזה, אז אני אגיד לכם שאני אשמח מאוד לדבר על זה אחר כך, אבל תרגישו בנוח לשאול. אז בואו נתחיל. So today I'm going to talk about verification of complex hyperproperties. And the problem of verification, or in verification, we are given some system and we want to make sure that the system is correct. And for the purposes for now, it could be any system that you think of, a distributed system, an infinite state system, some protocol, some algorithm, no matter what the system that you have in mind. Whatever this system is, we want to make sure that this system is correct. And by correct, I mean that it satisfies a set of properties that we are interested in. So when we say correct, with respect to what properties exactly do I want to check correctness? So traditionally, when we think of system correctness, we think of what we call trace properties. Trace properties are properties that we can look at each system execution separately, and from the correctness of each execution separately, we can conclude that the system is correct with respect to our property. So for example, if I want to make sure, so I'm given a system and I want to make sure that it always reaches a terminal state, then I can look at each execution separately, make sure that each of them reaches a terminal state, and therefore all executions reach a terminal state and I'm good. If I'm talking about functional correctness, so I want to make sure that my program or system computes some function, then again, I can look at each execution apart and make sure that my system computes the correct function on this execution. And if it's true for each execution, then it's true for the whole system. However, there is a wide set of properties in which looking at each system execution separately is not enough to express these properties. And these properties are called hyperproperties. Hyperproperties are system properties that relate multiple system executions. And this is a term coined by Clarkson and Schneider in 2008, but it stands for a very, very long established principle and concept from information flow security that you have to compare different executions in order to reason about, for example, information flow. So let's look at a simple example from the world of security policies. And this is an example that is called, the property is called non-interference. And here we have some system which has low security inputs and low security outputs. And it also have some internal high security inputs and high security outputs that are not observable to the user. And the property that we want to verify here is that there is no information leak from the high security inputs to the low security outputs. So what we actually want to say is that the low security outputs can only depend on low security inputs and not on high security inputs. And this property we cannot reason about if we look at each execution trace separately. So we have to compare different executions of the system in order to make sure that this property holds. And the way we do it is we say that for every two executions of our system, if they agree on the low security input, then they also agree on the low security output. So when I say for every two execution, it allows me to compare or relate different executions to each other, and then not just to say for every execution, if it gets 5 at the beginning, then it computes factorial of 5, but it allows me to look at different executions of the system and compare them. So as I said, hyperproperties are a very important concept in information flow. Spectra and meltdown are two attacks in which the attackers exploited information and different executions and information between different executions in order to perform the attack. So hyperproperties and the concept of comparing different executions is very essential to express security and information flow requirements. However, hyperproperties are not limited only to information flow and security, but they appear really almost everywhere. So I'm going to name just a few examples now. The first example is knowledge, which I'm going to explain a bit later. The second example is fairness. So if I want my system to be fair with respect to different inputs, for example, I have a woman input and a man input, and I want to make sure that my system is fair with respect to them, then I have to compare whatever happens for the woman and what happens for the man. So I need to do some comparison here. If I want to reason about causality, so if something caused something else, again, I need to check what happens if my cause does not exist and the behavior of the system in that scenario in order to conclude causal relationship. Robustness, so that the system behaves similarly when given similar inputs. Again, I will have to check executions with similar inputs and compare these executions, and then I can conclude that my system is robust or not robust. So hyperproperties are really everywhere, and therefore it is our responsibility to make sure that we can express these properties correctly, so we are able to reason about them and then provide algorithm to check them or to talk about them and so on. And in particular, I'm interested, as I said, in verification. So I'm given a property and I want to make sure that this property holds on the system. And here there are two challenges. And the first challenge is to provide an expressive and precise specification logic that expresses the properties that we are interested in. And the second challenge is to provide scalable verification algorithms that we can actually check that these properties hold on our system. And this is what I'm doing in my research in general. So I'm studying both logical aspects and algorithmic aspects of verification of hyperproperties. But in this talk, I'm going to talk mainly about our work from the recent CAV. This is a joint work with Raven Beutner, Bernd Finkbeiner, and Niklas Metzger. And this is about the verification of second-order hyperproperties. And what I'm going to show you today is a specification logic for complex hyperproperties, which again are properties that relate multiple executions. And these properties are, for example, common knowledge, which I will elaborate together with the knowledge example, and asynchronous hyperproperties, which allow us to talk about security and information flow and so on, but also in an asynchronous manner. So where different processes have different clocks, or we don't care exactly about what time something happens and so on. So I'm going to introduce you our new logic, hypersquare LTL. And I want to also provide a verification algorithm for this logic, so I'm able to verify these properties. However, this logic is very, very expressive and therefore is also undecidable. So in general, we cannot provide verification algorithms for it. What we are able to do is to use some approximations, and later you will understand approximations of what, but we're able to use approximations in order to verify these properties. So in this talk, I'm going to present you our hypersquare LTL. I'm going to use the example of knowledge and common knowledge, and then I will show you our approximation-based algorithm. And before I dive into the details of hypersquare LTL and so on, just a few words on the setting in which I'm concentrated in this talk. So our setting is of finite state systems. Here there is a simple finite state system. It has 3 states. In the initial state, we have some message that is not sent yet. Then our message can be sent and immediately be received, or it could be delayed for one time step and then received. And the executions, so we are interested in proving some properties over the system and over the system executions. And here, our executions are infinite executions. So if we get to receive, we will stay there forever, for example. So we have an infinite execution that just not sent and then received forever, or not sent forever, and all kinds of combinations of these. And we reason about discrete time steps. So here we have a prefix of an infinite execution, which has 7 time steps. In the first 4 time steps, the message is not sent yet, then it is delayed for 1 time step, and then it is received and it will stay there forever. So this is our setting, infinite executions of finite state systems. And to specify properties over such systems and executions, the most prominent logic suggested by Amir Pnueli in 1977 is LTL, linear temporal logic, that allows us to express temporal properties over infinite executions. So temporal properties are properties over these executions over time. So I can express, for example, termination. I can also express that something happens infinitely often, or that something bad never happens, and such properties. And LTL allows us to express trace properties. So properties over single executions of the system. In 2014, LTL was extended to hyper LTL. And hyper LTL features first order quantification over traces, and I will get to the details a bit later. So this is just an overview of what's happening here. Hyper LTL features first order quantification over traces in order to express hyper properties. So in order to relate different executions of the system. So for example, if we look at the non-interference example, the property was for every 2 executions systems, for every 2 executions of the system. So the for every 2 is a first order quantification. And it quantifies over the system executions. And by this quantification, we are able to relate different executions. So we can say for every execution, there exists another execution such that something holds, and so on. And indeed, hyper LTL is able to express properties like information flow, but also knowledge, and so on. Yet, first order quantification is not enough to express general properties that we're interested in. So 2 examples are common knowledge and asynchronous behaviors. And for that, we in our work introduced hypersquare LTL that features second order quantification over sets of executions in order to express the desired properties. So now what we're going to see is how we can express knowledge in hyper LTL, and what is the limitation that does not allow us to express common knowledge in hyper LTL, and therefore we need, so what is the motivation and the intuition beyond our extension to hypersquare LTL? Okay, so we start with the example of knowledge and then common knowledge and hypersquare. So now our setting gets a bit more complicated. Before we just had our finite state system, but now we also have 2 agents. We have a blue agent and a red agent. And each of these agents have some observations over our system. So the blue agent, while she knows what is the general system, so she has the gray graph above, but when she gets some execution, and we'll see it in the next slide, she cannot distinguish between a situation where there was a delay or the situation where the message was immediately received. So she can only tell whether the message was not sent or already sent. These are the observations of the blue agent. And similarly, the red agent cannot distinguish between a delay and not send. So he can only tell whether the message was not received yet or received. And now when we have observations of the agents of the system, then we are also interested in what they know that happens in our system. So let's start with a simple example. If I'm interested in whether the message was eventually received, and here I have an example for an execution, and I want to ask whether the message is eventually received on this execution, then the answer is yes. I can look at this execution. I can see that the message is received time step 6 or 7 and so on. And so the message is eventually received. And this is a property that I can express in LTL. This is a trace property because I can check every trace separately. Now I'm interested whether the blue agent knows that the message is eventually received. And for simplicity, I'm actually asking here if she knows that the message is received at time step 7. So the message is received, we see the execution, but actually to check if she knows something, then it's not enough to only look at this execution. What we have to do is we have to check all executions that she might think possible. So in other words, all executions that are indistinguishable for her. And if this property holds on all of them, then she knows that it holds. So in this example, she cannot distinguish between the case where the message was delayed in time step 5 or it was immediately received. So we have to consider these two traces. For her, these traces are indistinguishable because she only sees not send and then send. And so for her, these two possibilities are possible. And so we need to check both of them. And if our property holds on both of them, then we know it holds. And indeed, the message is received on these two traces, pi and pi prime, at time step 7. So this is a hyper property because we have to relate different executions in order to conclude the knowledge of the blue agent. And this hyper property states that for every trace pi prime that is indistinguishable for the blue agent, the message is received at time point 7. So this is very informal, but in order to verify or specify these properties, we actually need a logic that allows us to say these properties in a formal way. And the logic is hyper LTL. So I'm going to introduce hyper LTL. It will be a bit technical. But before, so hyper LTL is built on top of LTL. And therefore, let's see what an LTL formula is, or how we build LTL formulas. So an LTL formula could be just a proposition, such as received, sent, not sent, and so on. And this proposition can either hold or not hold on some time step of our execution. Then we can negate or conjunct properties. And then the interesting part here are the temporal operators. This circle is something holds at the next time step. And then we have until, so something holds until something else holds. And what you need to remember here, so you don't need to remember the operators, but we need to remember that LTL allows us to express temporal behaviors over infinite executions. So if we nest these operators, we can, as I said, say something always holds or happens infinitely often, and so on. And then we have hyper LTL that extends LTL by first order quantification over executions. So here I can say that there exists a trace such that something holds, or for all trace something holds, and I can nest them, so I can say exist for all exists and so on, and this is how I relate multiple executions. And now let's see how we express knowledge in hyper-LTL. So there is a formula here. The formula is equivalent to what there is in the text, in the natural language, and you can just choose whatever you feel more comfortable with. But this formula states that for every pi prime that is indistinguishable for the blue agent from pi, from the original trace, then the message is received at time 0.7 on pi prime. And also this indistinguishable we can express in hyper-LTL. We say that they agree on the observations of the blue agent. So the two traces agree both on not sent and on sent. So this is how we express knowledge in hyper-LTL. And now we're going to proceed to the example of common knowledge and see what's the problem there. Before we will proceed to common knowledge, let's look at both agents. So if I want to know whether at time 0.7 both agents know something, then what do I have to do? I do whatever I did for the blue agent, but now also for the red agent. So I look at my original trace pi, and I need to consider traces that he cannot distinguish from pi. And since he cannot distinguish whether on time 0.5 the message was delayed or not sent yet, then we also get this top trace in which the red agent might think is possible. And since on all these three traces now, so we need to now consider three traces because we're interested in the knowledge of both of them. On all of these three traces, the message is received at time 0.7, and therefore both agents know that the message is received at time 0.7. And now I want to ask whether it is common knowledge among the two agents that the message is received at time 0.7. So first of all, what is common knowledge? So formally, the definition of common knowledge is that both agents knows that both agents know that until infinity. So we just infinitely repeat this. And so just a second. And to express common knowledge, we would like to write, infinite formulas, but we can't. Why do we care about common knowledge? So common knowledge is important to achieve consensus or simultaneous actions or agreement on whatever is in this message and so on. So our discussion about common knowledge started from, a delay on Zoom. And then I was wondering whether my colleague heard what I'm saying and then whether he knows that I know and so on. And you sometimes want to make sure that so you reach this level of common knowledge, which I cannot repeat infinitely often, in order, for example, to achieve consensus. So this infinite repetition is some kind of a problem here. And in general, it is a known result that we cannot express common knowledge only using first order quantification over traces. So we cannot do that by means that I have already shown. And this is why we feature second order quantification in hypersquare LTL. Before I show you exactly how we do it, let's take another look at this behavior here. And when I try to do this infinite repetition, let's see what happens. It will not be infinite, don't worry. So we add more and more executions that are indistinguishable for one of the agents. So now the blue agent cannot tell whether the message was received or delayed at time 0.6. So I also get this trace. And then the red agent cannot know whether the message was delayed or not sent. Then I get this execution. And then the blue agent cannot tell or distinguish between the topmost execution and the execution in which the message is delayed at time 0.7. So in adding more and more indistinguishable traces to one of the agents, I got to a situation in my set of indistinguishable traces, I have also this topmost trace in which the message is not received at time point 7. So what we can conclude here that it's not common knowledge that the message is received at time point 7, because he might think that she might think that he might think, and until 7 iterations, that the message was not sent yet. It was not received yet, sorry. And what is important to take away from that is that to express common knowledge and also other properties of interest, we have our whole set of executions of the system. And in this set, we have some set here, the indistinguishable traces, that we want to somehow capture and then ask questions about. And in order to capture this set, we need to have the second order quantification. So this is indeed what we do in hypersquare LTL. We add second order quantification over sets of traces. So now I can say that there exists a set of traces such that something holds, or for every set of traces, something holds. And I can also relate traces to these sets. So I can say that my trace is in the desired set or not. And now I'm going to show you how we can express common knowledge in hypersquare LTL. Again, a very technical slide, but with also text explanations. So first, I say that there exists some set such that my trace is in this set. So I imagine in my head the set of indistinguishable traces, but I did not define it yet. And now I'm going to define it. So I'm going to say, this is the most complicated part, that if I have some trace tau prime that is indistinguishable from a trace that is already in my set, then tau prime should also be in my set. So if I already collected some indistinguishable traces and I find some other one that is indistinguishable, I have to add it as well. And after I have defined this set, then I can ask questions. For example, for all traces in this set are eventually holds. So this diamond is a syntactic sugar for eventually, and I can express it in with the temporal operators. And again, what is important to take away from here is that the second order quantification allows me to define the set of traces of interests, here all indistinguishable traces, and then to verify the desired property over the set. So here are eventually holds. So this is what hyper-LTL allows us to do, to define sets and then ask questions about these sets. And using this second order quantification, it allows us to express many interesting properties. I want to mention that there are domain-specific specifications or specification languages for the properties I showed here, so for common knowledge and for asynchronous hyperproperties and for other properties as well. The limitations on the logical side of these solutions is that they are domain-specific. So they do not allow us to understand relations between different properties from different domains and so on. But they only approach a very, very specific problem. So here you see like 3 bullets of asynchronous. Every such logic captures a very, very specific solution or behaviors of asynchronicity. And what hypersquare LTL allows us to do is to provide generic way to reason about a very, very large set of properties. So now I'm not limited to only one notion of asynchronicity or to only common knowledge, but I can express a very wide range of properties. And moreover, it allows me to understand connections between these properties that I could not understand before. So when you think of asynchronous behaviors alone, or when you think of common knowledge alone, or for other properties just in that specific domain, you don't immediately see the connections between these properties. And here, once we started playing with them and showing that they are expressible in hypersquare LTL, We also found very similar behaviors of these properties that allows us to provide also verification algorithms based on these similar behaviors. So this is what I'm going to show now. So we know what hypersquare LTL, it allows us to express interesting properties in a generic way using second order quantification. And now I'm going to talk about our verification algorithm. So first, let's remember that in verification, we have a system here, a finite state system, and we have a property given in some temporal logic. And we want to make sure that our system satisfies this property. And just so we have some context on the hardness of this problem. So for LTL specifications, this problem of verification to verify a system versus an LTL specification is in P space. To verify a hyper LTL specification, it's Tower exponential. It depends on the number of quantifier alternations. Actually, in practice, it's usually not as hard because the properties have only a few alternations, but in general, this is the complexity, but it's still decidable. Hypersquare LTL, as I said, its verification problem is undecidable. And therefore, we need to come up with some solution that allows us to still provide answers, but we want to somehow manage this undecidability somehow. And for that, what we did is to identify a fragment of hypersquare LTL. We call it the fixed point fragment. And this is a syntactic fragment of the logic that still captures all properties of interest for us. Its verification is still undecidable since it's very expressive. But what we can do here, the fixed points, which I will explain soon, allow for sound approximations of the second order sets. So we have second order sets in hypersquare and we can approximate them in a sound way. And then we can provide some approximation-based algorithm. So a few words about the least fixed point fragment. Let's go back to the common knowledge formula or explanation. And what we see here is that we start with our trace pi and then we add traces. But if we already have in our hands the set of all indistinguishable traces, and then we try to add another trace to this set. So we capture one and we say, okay, if it's indistinguishable, then I need to add it. Then this set will not be changed because we already had the set of all indistinguishable traces. So a fixed point is a set for, the purpose of this talk is a set that remains the same when I try to add traces. So if I already have the set of indistinguishable traces, trying to add traces will not change it. And the least means that this is the smallest set such that it remains the same when trying to add traces. And since I have the smallest set, then it is also a unique set. And we show that indeed this fragment captures a lot of properties of interest, in particular the ones that I mentioned here. And what fixed points allow us to do is first, we have unique sets instead of arbitrary set quantification. So arbitrary set quantification, for every set there exists another set and so on. It's something that algorithmically is more complex than having a unique set that you reason about. And second, fixed points have a very nice feature that they allow constructive computation, both of over approximations and of under approximations. And we're gonna use this in our algorithm. So if you go back to our example, we have our set, our desired set in our head of indistinguishable traces that we want to capture somehow. The traditional way to capture temporal properties is using automata constructions. So we want to come up with an automaton for our desired set of traces. But we cannot have such an automaton. So what we are going to do is we are going to compute an over-approximation. An over-approximation is a set that contains the real set that we're interested in. And we're going to also compute an under-approximation, which is a set that is contained in the set that we are interested in. And after we have computed both an over-approximation and an under-approximation, we can choose what set, what approximation, what automaton we want to use in the following way. So if my formula asks for every trace in the set something holds, then I'm going to use my over-approximation. And the reason is that if I'm able to prove that something holds for every trace in the bigger set, then it for sure also holds for every trace in the smaller set. And similarly, if my formula states there exists a trace in my set, then I'm going to use the automaton for the under-approximation, because if there exists a trace in the smaller set, then obviously there exists a trace in the larger set as well. So this is the general idea behind that. I'm not going to get into the details of how we compute these over and under approximations, and I would like to explain later. But I do want to generalize this not only for one set, but for general formulas, general hypersquare formulas. So here we have a general formula. Could be very long, but what you see here is first order quantification over traces. So there exists some trace, and for every trace in X1 and so on. X1 and XK here are second order sets that are defined, as we said, using some formula that defines a fixed point. And psi is whatever we want to verify on the sets that we defined. So here, for every trace, the property, the message is eventually received. But in general, what we care is that we have here sets that we can compute over approximation to and under approximation to. And this is what we do. For each of the second order sets, we compute both an over approximation and an under approximation. And then we choose them, as I said, according to the first order quantification. So whenever I see sum for all trace in X1, then I will choose the over approximation. And whenever I see there exists a trace in some set, then I will choose the corresponding under approximation. And now I have automata for all of my sets that approximate my sets. And now what I'm going to do is use first order model checking, so hyper LTL model checking. And there are algorithms for hyper LTL model checking, and try to prove my formula. And if I was able to prove my formula because I chose the over and under approximations correctly, then if I'm able to prove, then the formula for sure holds and I'm done. If I was not able to prove, then I can also try to refute my formula. So I do exactly the same, but I negate my formula and see if it holds. And if it holds, then I was able to prove that my formula does not hold on my system. So I can either prove or refute my formula. And if I could not prove the formula and could not refute the formula, then I need to compute the second set of approximations and so on. So I need to refine my approximations. That means that I'm both enlarging my under approximations, so I'm getting closer to the real set from below, and I'm making my over approximations smaller and getting closer to the real set from above. So an overview of the algorithm is that for each second order set, we compute both an over approximation and an under approximation. Then we choose it according to the first order quantification, and then we apply hyper LTL model checking. And the challenges here are first how to compute over and under approximations, and how to capture exactly the relations between first and order variables, and and second order variables, and third, to perform first order model checking. So first order model checking we perform using existing algorithms. We implemented them to work with our setting, but there is nothing new there. What is very interesting is how you compute over and under approximations, and how you relate between, how you capture in the automata the relations between the variables. So in our implementation, we use automata learning to compute over approximations, and we use the iteration approach to compute under approximations. And we tried it on a set of examples. I'm going to go over them not too much in details. What you see here on the left is an example of common knowledge. It's similar to what I've showed you here, but here we wanted an example in which we can prove that common knowledge holds. And therefore our question was something like whether it's common knowledge that the message was not sent at the first time step. And then depending on what size of traces you begin with, so how long you postpone the sending of the message, it takes us longer to prove that common knowledge holds. So these are the ends here, how far we delayed the message. And indeed, we were able to prove that common knowledge holds on all of these examples. So we were able to reach the fixed point and prove on it. And the second table is an example of the Muddy Children puzzle. So in the Muddy Children puzzle, very, very high level, we have n children, and some subset of them has mud on their forehead. And then in rounds, they need to together or to conclude whether they have mud on their forehead or not. And actually, it is known that it takes, if you have 3 children, then it takes 3 rounds to conclude that you have mud in your face. And then actually it's common knowledge for everybody exactly how many children has mud on their face. And here is, so we played with this a bit. We were able to prove that it is not common knowledge for less than 3 time steps if we have 3 kids. So similarly for 4 and so on. And the numbers below are the times that it took us to prove that. And we implemented it on asynchronous hyperproperties and properties from trace theory, but I leave it to you. And now I'm gonna go back to this slide once again. So as I said, there are domain-specific specifications and also domain-specific algorithms for these properties. And the limitations here are, as I said, both that they are domain-specific, so they are not exploiting similarities between different properties, but also that all of these all verification algorithms that already exist are limited only to decidable fragments of the logic, while our algorithm can actually handle properties that are beyond the decidable fragment. So our algorithm will not always terminate, but it can be applied to undecidable, to the undecidable fragment and to try to solve this and to sometimes terminate, which is already generalizes what already exists. So to summarize, we've seen second order hyperproperties. We've seen second order hypersquare LTL, which is a specification logic for second order hyperproperties, and an approximation-based verification algorithm for it. And in this context, we are also working on understanding the hierarchy of second order hyperproperties and what exactly we need to express what property. And in the algorithmic side, we're working on monitoring second order hyperproperties. So what I've showed you today is, given a system, prove that the property holds on this system or not. But for that, we have to have the system. in monitoring, we either don't want to use the system because it's too big, or we don't have access to the system at all. So the system is a black box for us. And then we just see the executions. So we'll observe executions of the system. And in our paper, we showed a monitoring approach so that it allows us to verify these properties only based executions that we observed. And we are also, since in monitoring, you observe execution, so you only observe finite executions. You cannot observe anything that is infinite. And we are also working on the complexity of the problem over these finite executions. And now, just before I summarize, I want to talk about a very, very high level on a different application. So I take you back to one of my first slides in which I said that the challenge is in providing expressive specification logic and in providing scalable algorithms. And I want to give you some overview. So if you're interested to talk later or something about my work in causality. So in causality, we're interested in explaining temporal behaviors of systems using counterfactual reasoning. And so, for example, if we suspect that their request at the first step caused some grant later, then we will negate it and check what happens. This is very, very much simplification of our work. But in general, we're interested in formalizing causality definitions to the setting of reactive systems and infinite executions, and to provide algorithms that verify causes. So if you suspect that this request is a cause for something, then we can verify that it is or not, and find causes. So just give me a behavior of a system and I will explain it to you. So I'm very interested in causality and I would be very happy to talk. And now I reach the end. So what we've seen today is hypersquare LTL and its verification algorithm. But in general, it falls in the category of understanding landscape of hyperproperties. How do I express properties of interest in a way that allows me to reason about them and to provide algorithms for them? And in particular, I would be very interested in applications in distributed systems. So both common knowledge and asynchronous behaviors and so on are properties of distributed systems and of communications, communication protocols. Also applications in robotics, we have some examples of planning and so on in this scenario. And as I said, also in the context of causality. So thank you very much. That's it.
Thank you for that.
Thank you very much.
Thanks.
שאלות למישהו? לי שאלה, מה בעצם הגרנטי שאת מקבלת מה-approximation אלגוריתם? אז הבנתי שהתהליך הזה הוא לא בהכרח יתכנס.
נכון.
אבל מה כן, יש איזשהו גרנטי? כמה זמן זה ייקח או משהו כזה?
אז אם הפיקס פוינט שלך זה משהו שאפשר להגיע אליה בזמן סופי, אז הגרנטי הוא שנגיע אליה בסוף בזמן סופי שאפשר לחשב אותה. אם יש לך אפשרות, אז זה תלוי בעצם באובר ואנדר אפרוקסימיישן ספציפית שאת משתמשת בהן. כלומר, אם את יודעת לחשב אובר אפרוקסימיישנס מדויקות מספיק, אז עקרונית את יכולה, אבל באופן כללי לא.
אוקיי, אז זה משהו שכאילו תלוי באינפוט של הבעיה, ואז...
תלוי באינפוט, כן, וזה גם תלוי איך אנחנו מחשבים, כאילו ספציפית, חישוב של האובר ואנדר אפרוקסימיישן.
אז אם אפשר לשאול בהמשך, אז בעצם אבל, איך את מתחילה? כלומר, מאיפה את בוחרת את הקירוב, ואז את אומרת כל פעם שאני לא מצליחה, את מהדקת את זה טיפה יותר, נכון?
כן.
אבל את מקבלת איזשהו משהו, איזשהו לגבי סוג הקירוב, או כמה, נגיד איזשהו פרמטר תיאורטי כזה, משהו שאפשר לעבוד איתו?
קירוב הוא לא שזה לא מדויק, אלא כלומר, לא מדויק במהותו, כי זה לא בדיוק הסט שאני מדברת עליו, אבל כאילו הגרנטי שיש לי על האפרוקסימיישן זה שאני מוכלת בסט שלי ושאני מכילה את הסט שלי. אני מתחילה בדרך כלל, כאילו ההתחלה של החישוב שלי, כרגע איך שאנחנו מחשבים את זה, ההתחלה של ה-under approximation זה בדרך כלל או trace אחת, או temporal, כאילו איזושהי temporal property ב-LTL, כאילו איזושהי trace property שתופסת איזשהו set. אבל זה כאילו הנקודת התחלה שנתונה לנו על ידי הנוסחה, ואז אנחנו מחשבים. עכשיו, יש שיטות של להאיץ את החישוב הזה ובאמת להתקרב יותר מהר, או כאילו לחשב approximations בצורה יותר מהירה. אנחנו עובדים עליהם כרגע, כאילו אני עובדת על זה עם סטודנט, זה עוד לא משהו שנימשנו.
יש, אבל אם אני מבין נכון, Square LTL מכיל גם את Hyper LTL, נכון?
נכון.
אז אני בעצם, ול-Hyper LTL יש אלגוריתמים מדויקים, אז
נכון.
אני יכול להשתמש בזה בתור אלגוריתם קירוב, נגיד יותר מהיר, ל-Hyper LTL, אם אין לי כוח לחכות לאלגוריתם מדויק יותר?
לא, כי האלגוריתם שלנו הוא משתמש, כאילו הוא לא עושה את Hyper LTL יותר מהר.
לא, אבל אם אני רוצה קירוב, נגיד נתתי לך תכונת Hyper LTL, ואני לא רוצה דיוק שלה, אני רוצה קירוב, אז יש איזה סיכוי שהאלגוריתם שלך יכול לתת לי את זה?
וואו, זאת שאלה ממש טובה. זה אומר שאתה צריך לייצג את הסט של טרייסס שאתה מתעניין בו איכשהו, כאילו אני צריכה איכשהו להגיד הסט שמעניין אותי הוא זה, ואז עליו אני אעשה קירוב, ואז בעצם כאילו אני לא בודקת את כל המערכת, אלא רק משהו של המערכת.
כי אכפת לי נגיד רק קירוב, לא אכפת לי ממש דיוק, אני רוצה קירוב מהיר יותר מאשר דיוק.
אז אני אחלק את התשובה שלי לשניים. מבחינת קירוב מהיר יותר, הרבה פעמים דווקא לעבוד כאילו על כל המערכת שאתה עושה ב-Hyper LTL, יהיה לך יותר קל מאשר לחשב איזשהו תת-סט שלה ולעבוד עליו, אבל יכול להיות שזה יעבוד, כאילו לא ניסיתי את זה בכלל וזה רעיון די מגניב, לנסות להשתמש בסטים שיש להם התנהגות מאוד פשוטה, ורק להוכיח עליהם דברים, ואז לקבל גרנטיז מסוג מסוים, זה ממש רעיון מגניב. והדבר השני שהוא לא ממש מה ששאלת, אבל זה קצת הזכיר לי שאנחנו בעצם, מה שגם אני עובדת עליו עכשיו אגב עם סופרטיק, זה לקבל קירוב לתשובות שלנו. כלומר, אם אני, לא אכפת לי אם הוא יודע, אלא אני רוצה שהוא ידע בהסתברות גבוהה או משהו כזה, אז זה בעצם כאילו קירוב להייפר LTL, בעזרת הייפר סקוואר LTL, אבל מה שזה נותן לי זה לא יותר מהר, אלא תשובה לשאלה אחרת.
אוקיי, בסדר. טוב, אנחנו נמשיך לדבר על זה, נשמע ממש מעניין. אוקיי, עמרית, הייתה צריכה לעזוב, אז אני אקח אז אני אקח את זה מכאן. יש למישהו שאלות נוספות?
כן, בבקשה.
כן, בבקשה.
דיברת במצגות הראשונות בהקשרים של מלדאון וספקטר, את יכולה אולי קצת לתת דוגמאות או לפרט יותר איזה תכונות מעניינות אפשר להגדיר על המערכת בהקשר של למנוע ספקטר או מלדאון? כלומר, איך זה יכול לראות?
זה השתמשו בהשוואה בין תזמונים של כל מיני שימושים בכל מיני משאבים כדי להבין מה קורה. באופן כללי כדי למנוע, אז זה בפן של security בכלל ו-information flow בכלל, אז יש ממש טווח רחב של תכונות שאפשר, שהן hyper properties במהותן, והרבה מהם אפשר גם להביע בלוגיקות שאני דיברתי עליהן כאן, והרבה צריך רחבות מסוימות, אבל המהות היא שאתה משווה בין חישובים שונים. אז למשל, אתה רוצה למשל להגיד שלאטאקר מבחוץ, שני החישובים נראים אותו דבר, ואז הוא לא יכול להשתמש במידע מבפנים כדי לעשות משהו. אז אני אומרת, כל דבר שהוא זמין למישהו מבחוץ, למשל, התזמונים, אם זה זמין למישהו כאילו שיכול להסתכל על המערכת שלי, אז התזמונים יראו אותו דבר בכל שני חישובים שלי של המערכת, או בכל שני חישובים שהאינפוט הציבורי, הוא אותו דבר. דברים כאלה, כל אלה זה הייפר פרופרטיז מאוד פשוטות במובן שהן מאוד אלגנטיות, כאילו להביע אותה, מאוד קל לכתוב את הנוסחה, וזה ממש נחמד. אני אוסיף, כאילו, אני מקווה שזה לא יהיה טכני מדי. מה שאני דיברתי עליו עכשיו זה כאילו אם משהו קורה או לא קורה, נכון? כאילו אמרתי send או not send וכאלה. אבל יש לוגיקות שמרחיבות כאילו לוקחות את hyper-LTL או את LTL ומדברות על ערכים שהם לא, כאילו שהם רציפים או שהם לא בוליאנים. ואז זה ממש מאפשר לנו להגיד את הדברים האלה. כאילו אני באמת יכולה לדבר על תזמונים. שני התזמונים יהיו אותו דבר בשני החישובים האלה תמיד. אז כן.
תודה.
אוקיי, שאלות נוספות? אם אין, אז תודה רבה. אדר, המון תודה, ולהתראות בקולוקיום הבא.
להתראות, תודה רבה לכם.
ביי
תודה
ביי.
רבה, להתראות.
ביי, להתראות.